So this video, we're going to discuss equilibrium equations and equilibrium constants. So chemists, we typically like to quantify things, all right? And I mean, simply because when we're putting numbers to it helps us to understand what's really going on in a much deeper level, much more than what oftentimes qualitative analysis can give us, all right? And so, like, for example, if we have this equation here, A plus B yields, or in equilibrium, C plus, actually I'm not going to use CC. Those C's look too familiar, too alike. Let's do D plus E. Now these lowercase letters here represents the coefficients. All right. So if we have a real chemical equation, that the lowercase letters represents the coefficients, while the uppercase letters represent the actual substance, the actual particle itself. All right. Now, as I said, for equilibrium, we like to quantify it. And oftentimes, when something has reached if a reaction has reached equilibrium, what we would like to know is what is the ratio of the products to the reactants. All right. And this tells us a lot. It helps us to understand the overall dynamics and the dynamics of the chemical reaction itself. We understand the nature of the chemical reaction and what happens when it reaches equilibrium, okay? And so when it reaches equilibrium, us chemists like to know what is the ratio between the reactants or products. So in other words, we like to know, or showing you, can't find the eraser. We like to see the ratio of the products to the reactants. All right. Okay. And this ratio of the products over the reactants, we call it the equilibrium constant, or K. All right. And so K stands for equilibrium constant. All right. This right here is our general equilibrium equation, where K is basically the ratio of your product's concentration over your reactant's concentration. So another way that we typically will write this is the concentration of your products divided by the concentration of your reactants. All right, as I said, is equal to K. So what does this tell us? All right. Now, if you think about it as in terms of fraction, because that's essentially what this is really just a fraction, right? Depending on what K is, you could tell if the equilibrium is either reactant favored or product favored, okay? And so, for example here, if K is greater than 1, then it's going to be product favored, right? The equilibrium is going to be product favored. So that simply means when the reaction has reached equilibrium, there's a higher concentration of products than reactants. And that kind of makes sense when you think about this from a point of view of a fraction. All right, for a fraction to be greater than 1, the product has to be a larger number, or the magnitude of the product must be larger than the magnitude of the reactants. The number of the product must be higher than the number of the reactants. So, like, for example, if you had something like 5/2, right, then this number is going to be greater than 1. So thus, product favored, right? If you have a K that's less than 1, then we say that the equilibrium is reactant favored. All right, which, once again, if you think about this as a fraction, that makes sense, right? Because if not that. All right, so if you consider the this fraction because between products over reactants, and you have something like if the product's concentration is 1 and the reactant's concentration is 5, well, 1/5 is less than 1, right? That number, that's what, 0.20. All right, so that's less than 1. So that tells us that at equilibrium, there's just a higher concentration of reactants compared to concentration of products. Okay, so that's the way that we essentially look at that. Now, let's kind of go back to our equation I was showing you a little bit earlier, and I'm going to erase this. All right. So let's look back at this equation I was showing you earlier, where this is our generic equation where you have AA plus BB. It's in equilibrium with DD and EE, right? And as we said earlier, K, or the equilibrium constant, is the concentration of your product over your concentration of your reactant. Okay, so now I could go ahead and take this equation here, this chemical equation, and apply it to the equilibrium equation. All right, and this is how we do this. Okay, so we have the concentration of D, it's a product, okay, to the power of the coefficient times the concentration of E, which is another product, all right, to the power of its coefficient, divided by, so now we're division here. Now we're going to look at the reactants and the concentration of the reactants. So we have the concentration of A to the power of its coefficient times the concentration of B to the power of its coefficient. All right. And so this is basically how this works. Now, one thing that I want to note is that K is very much so dependent on the temperature. All right, so the temperature has to be constant throughout the chemical reaction. Once you change the temperature, you're definitely changing K. All right. There's typically no units to this. All right, the units are oftentimes omitted, so it doesn't mean for anything. And when it comes to what you place in here as for products and reactants, all right, the only thing that can undergo equilibrium and or the types of substances that we tend to omit from equilibrium expressions or equilibrium equations. Sorry, tongue-tied there. All right, we never include solids or liquids. All right, we do not include solids or liquids. So you have to really pay attention to the state of matter of each of these substances. So if it's aqueous or a gas, then we will include it in here. All right. If it's a solid or a liquid, we will omit it altogether. All right. So let's look at an example of writing these equilibrium expressions, and that's how we call them, using an actual real chemical equation. All right. So here's a chemical equation where we have vapor, water vapor, plus methane gas. All right, and this reaction is in equilibrium to form carbon monoxide plus hydrogen gas. All right, and so what we want to do is write the equilibrium expression or equilibrium equation according to this reaction here. All right, so here's my equilibrium constant, and it's equal to, all right, so recall that over here are my products, over here are my reactants, and I'm gonna kind of write this on top, in that the equilibrium expression is the concentration of my products over my concentration of my reactants. Okay, and so let's go ahead and let's write this out. All right, so my products here, I have the concentration of carbon monoxide, and its coefficient is 1, so that's the first part. We don't really need to write that. all right, times the concentration of hydrogen gas, and it has a coefficient of 3, so this goes to the third power. All right, divided by or over the concentration of water, H2O, so this only has a 1, so that's okay. So it's H2O to the first power, and then of methane, and this also has a coefficient of 1 as well, so times CH4 to the first power. So this is the equilibrium expression for this chemical equation. So let's look at this example problem, okay? Or another example problem. So in the reaction of Cl2 with PCl3, the concentrations of the reactants and the products were determined experimentally at equilibrium, and it was found to be 7.2 moles per liter for PCl3, 7.2 moles per liter for Cl2, and 0.050 moles per liter for PCl5. Okay, and so let's go ahead and look at the chemical reaction, the chemical equation. So let's kind of write this out, where we have PCl3 gas plus Cl2 gas are in equilibrium of PCl5 gas. Okay, and it tells us that the concentration of PCl3 is 7.2, so 7.2 molarity. The concentration of Cl2 is also 7.2 molarity, and the concentration for PCl5 is 0.050 molarity. All right, and so what we're going to do is we're going to calculate the equilibrium expression for this chemical reaction. Now remember, K is equal to the concentration of your products over the concentration of your reactants. Is always probably a good idea to write the equilibrium expression first with the substances before we put in the numbers. All right, so our products in this case is the concentration of PCl5, and if we notice, its coefficient is 1. All right, so it's really just to the first power here. All right, times or over the concentration of PCl3. All right, in this case, hopefully you notice that the coefficient is 1. All right, so it's to the first power times the concentration of Cl2, all right, or chlorine. And once again, if you notice, its coefficient is really just 1 as well. Okay, now we're going to just plug in these numbers accordingly, what we got. So we have 0.050 divided by 7.2, I'll put this all in parentheses, times 7.2. All right, and so when you plug this into the calculator, we'll get 9.6 times 10 to the negative 4. All right, couple of things to address. Number one, equilibrium constant doesn't have a unit. All right, so don't try to force one on there. Okay, number two, when you're looking at this number here, all right, you can make a couple of predictions about this chemical reaction. All right, well, first of all, this number is less than 1. So if it's less than 1, that simply tells us that there's a higher concentration of reactants than products when this substance has reached, or when this chemical reaction has reached equilibrium. All right, and so those are the things that you could definitely pick up by just looking or figuring out what exactly is the equilibrium constant. Okay.